Good morning. Today we have two things: a Codeforces round, which is round 774, and a guest, at least for the intro.
Good afternoon.
Where am I? Where's the? Oh, there's right there. Yeah.
Hi guys.
So that's my brother Jonathan. He doesn't actually do programming, but he's visiting Seattle, so I thought I'd say hi. All right, and the contest just started. So goodbye, Jonathan.
Bye. Have fun.
Time to go do the contest. All right, here we go. Where's my mouse? Here's my mouse. Okay, not a great start, but we'll make it work. Lewis has a sequence of n+1 integers. For each I, it's guaranteed that this element is between 0 and n, less than n, or it's equal to n squared. He's calculated the sum of elements in the sequence and called this value s. He's lost the sequence but remembers the value of n in s. Can you find the number of elements in the sequence that are equal to n squared? We can show the answer is unique under the given constraints. It's the sum over n squared. So we're given, what is this? We have n and s. So 12 over 4 squared is 3. Yep. Copy, paste, there we go. I'll explain why that's true after the contest with the solutions to all of the problems that I don't know how to solve. Looks like we got it right. Let's move on from B. Quality versus quantity. Oh, we don't have 0 either. Darn, that's a little annoying. Okay. Well, we have the lights, right? So the lights will check for us. You're given a sequence of n non-negative integers, a1 to an. Initially, all elements of the sequence are, initially all elements of the sequence are unpainted. You can paint each number red or blue, but not both, or leave it unpainted. For a color, count of C, but we can paint each number red or blue, or leave it unpainted. Okay. What is the underline, upper line thing? Okay, anyway. So for a color C, count of C is the number of elements which are painted that color, and sum of C is the sum of elements which are painted that color. Okay. For example, we can leave it unpainted. So we can do 2, 3, 6, okay? Is this for like colorblind people? All right. Sum of red is 6. Sum of blue is 5. Count of red is 1. Yeah, okay. Determine if it's possible to paint the sequence so that sum of red is bigger than sum of blue and count of red is less than count of blue. Yeah, so you just paint everything blue and then replace the most valuable things with red. So yeah, prefix of blue, suffix of red, and you can even determine the unique prefix. Okay, this is kind of boring. And then we'll say for int I equals 0, I is less than or equal to n divided by 2. Well, I guess I is less than n. If I is less than or equal to n over 2, then s1 plus equals 8i, else s2 plus equals 8i. And then sys out, s1 is less than s2. If so, yes, otherwise, no. All right, so does this work? When n equals 2, this will be 1. When n equals 3, 3 over 2 is 1, so 0 and 1 are on the left, yeah. So this should be correct. Submit. Let me submit. Can I please submit code? Thank you. All right, let's move on to m1.codeforces.com. I don't know why. I really don't think it's my internet, but it's possible it is. Who knows? Okay, and we'll watch the lights here for results. Okay. Let's see. Factorials and got it wrong. Okay. Wrong answer. For even, there's a better way of doing it. Yeah. Okay. So if you have 4 things, let's do this. 1, 2, 3, 4. This is possible. So I say no, the answer is yes. So what do we do? Subtract this one if yeah, okay. Or subtract, okay, so we want the sum to be bigger, so yeah, we subtract this one. So if n mod 2 equals 0, s1 minus equals a at n over 2. That was kind of a dumb mistake, but should be easy to fix. Yeah. Okay. Pretty sure that's right then. Why can I not submit? Here we go. Okay. I just see. A number is powerful if it is a power of 2 or a factorial. In other words, a number m is powerful if there exists a non-negative integer d such that m equals 2 to the d, where m equals d factorial, where d is 1 to d. Okay, we understand. For example, 1, 4, and 6 are powerful numbers. You're given an integer n. Find the minimum number k such that n cannot be represented as the sum of k distinct powerful numbers. Oh my goodness, this sounds hard. Oh, factorial probably doesn't matter. Maybe it matters. Whoa, this is a non-trivial problem. Okay. Oh, n can be represented. Find the minimum k such that n can be represented as the sum of k distinct powerful numbers. Okay, so not as hard. So we can always do it in like log n, worst case, just like the bit count. So that's one observation. So we can, where did my C go? We can always do long that bit count of n. Otherwise, there are some factorials. So we can brute force which factorials are interesting. Yeah, so it's actually very easy. Never mind. Okay. Darn. There are probably like 10 factorials, right? So, or I don't know, 15 maybe? So 2 to the 15 times 100. That's fine. Long n equals this. This dot next long. And then long array factorials equals this will be an array list. Array list long factorials gives you array list. So then, hang on, let me make sure that's not my brother being locked out here or something. Okay. He seems to know how to get through doors, so we're good. Long product, well, yeah, prod equals 1. So we don't care about 0 factorial, we don't care about 1 factorial, we don't care about 2 factorial. So 6 is the smallest relevant one. Yeah, 4 and I equals 3. True I plus plus. Prod is greater than n. Okay, then break. Otherwise, prod times equals I. And factorials dot add prod. Okay, so we have all of this. None of these will be powers of 2 because they all are a multiple of 3. And we're good. So 4 int I equals 0. I is less than 2 to the factorials dot size, I plus plus. We'll call this mask. And then long sum equals n. I equals 0, I is less than factorials dot length or dot size plus plus. With mask and 1 to the I or 2 to the I is not equal to 0, and sum minus equals factorials dot get I. Okay. If sum is less than 0, then continue, and then long ans equals long dot max value. This up the answer. Ans equals max dot min of integer dot bit count of mask plus long dot bit count of sum. We should be good there. 2, 3, 4, 1. This is a terrific problem to teach people bitwise operations. Very good problem. Glad I have this in my arsenal. Instructive wise, this is very useful. Yeah, it hits. And I'm wrong. Okay. Why am I wrong? If it cannot, it always can. Oh, can it not? Yes, it can. Surely it must be able to. What about 4? 4 is just power of 2. Okay, this is along. So 24 is a, that's not right. Wait, what? 24 is 6 times 4? Oh, I have 4. Lots of wrong answers today. Not the end of the world. Okay. With the weight of a tree. I thought I said width of a tree, and I'm like, I've already done this problem. It's circumference of a tree. Anyway, you're given a tree. If you haven't done my tree basics set, I would highly recommend. Lots of very interesting problems there, interesting techniques, very useful learning experience, in my opinion. And we got it. You've got a tree of n vertices, numbered 1 to n. A tree is a connected, we know what a tree is. Thank you very much. For each I from 1 to n, let wi be the weight of the ith tree, of the ith vertex. A vertex is called good if its weight is equal to the sum of weights of all its neighbors. Okay, so we have a bunch of nodes with weights. It's good if it's equal to the sum of weights of its neighbors. Okay, so we can initially determine which nodes are good. Initially, the weights of all nodes, never mind. Initially, the weights of all nodes are unassigned. Assign positive integer weights to each vertex of the tree, such that the number of good vertices in the tree is maximized. If there are multiple ways to do it, you can find the way that minimizes the sum of weights of all vertices in the tree. Okay, so these all are positive, right? Yes. Okay, so they're all positive, which means you can't have both nodes on an edge, which means 2 color. Ooh, doesn't mean 2 color. Does it mean 2 color? Oh, oopsies. Okay. It might not. Wait, so yeah, it might not mean 2 color. But it's the classic tree DP, right? You either pick this node or you don't. So you can, so example of why it's not 2 color. You've got this, what the heck? Okay. You've got this case. So 2 coloring would pick, like you'd 2 color these 3, but you can get 4. You can get this one, this one, this one, and this one. So it's not 2 color. Yeah. So we'll do like some DP at node, and then whether it's like allowed. And this will equal max nodes, comma, min cost, I guess. All right, there you go. So we'll do that. Should be pretty easy. Static class node, static class ants. So this will be int max nodes, int min cost, public ants better. So ants A, ants B. Classic, if A is null, return B. If B is null, then return A. Then if A dot max nodes is not equal to b dot max nodes, return a dot max nodes is less than b dot max nodes. If that's the case, b otherwise a. And then a dot min cost is not equal to b dot min cost. Well, otherwise just return b dot min cost is less than or equal to a dot min cost. That's the case, b otherwise a. Okay. So we'll have an ans if allowed, and then an ans if not allowed. And then we'll have an array list of node adjacency, there's new array list. And then we'll have public void go allowed. Go not allowed. So if allowed is not equal to null, and return if allowed. We'll do this in a minute. Okay. So this will return an ans as well as this. So okay, yeah. Ans if take equals new ans, and then for, oh, this also needs the parent, so node root. Yeah, that's all that matters. For node nn in adjacency, we want all the ones that aren't the root, so if nn is not equal to root, then we'll say if Alright, so then we'll say if take plus equals kid ants dot max nodes. If take dot min cost plus equals kid ants dot min cost. And so if take dot max nodes plus equals 1. If take dot min cost plus equals this, or plus equals adjacency dot size. Okay, then we add all our kids. And then we'll say ans if don't equals go not allowed. And then return, okay, so we'll say return, yeah, if allowed equals better of if take, and then if don't. Okay, and then this one is quite simple. So this one is ans. Okay, so yeah, we still need where we come from. And then we'll say if not allowed, not equal to null, then return if not allowed. Otherwise, if not allowed equals new answer. And then we essentially do this. The problem is all of these kids are all of these kids, we need to have them be allowed because we are not allowed. I think we're good. Okay, so then we need node array nodes equals new node array n. Where is the problem statement? We're given all the edges. Okay. Okay, so we've got these, and then we need to get the answer. Oh, do we have to print it? What do we print? Maximum number of good vertices and minimum possible sum. Okay, that's annoying. Yeah, fine. Then we have to actually do it. Okay, fine. Ugh. All right. So ants equals nodes at 0 dot go allowed. So ants dot max nodes plus ants dot min cost. All right, and then we need to rebuild this in a moment, which we'll do. Not true. Single test case. $20. Now, how does that happen? $20 nodes? X nodes plus equals 1. Yeah, the answer is 3. You take 1, you take 3 and 4. Wait a minute. Oh. Okay, so if there are 2 nodes, we'll get it wrong. Sneaky. Yeah, look at this. Okay. And then we have to rebuild. Okay. So yeah, how is this wrong? I guess let's for each node print what the score is. Okay, and then we'll say oh, that's weird. How do we get here twice? Oh. Yeah, so this is this. Wow, that's weird that actually terminated. And this is this, okay. 3, oh, 4. Okay. All right, so yeah, so some slight logic bugs here. If we're allowed, max cost is this. What if we're not allowed? Okay, so if not allowed dot min cost plus this, because we have to buy ourselves. Do we have to buy anything else? No, just ourselves. So we buy just ourselves here. Otherwise, we buy enough to make us special here. And then we should be good. Yeah? Okay, so build back. Public. Do we want to build back? I guess let's just do, okay. Public void build back allowed node root, and then public void build back not allowed. Okay, so Boolean taken is false. No. So this will be just this. Okay. All right, so we don't care about this. We don't care about the return value. We don't care about the answer. We just do nn dot build back allowed. Pass in this. Okay. All right, so this part is the interesting part. If allowed, we don't care. Yeah, so if better, if take, if don't equals if take, then taken equals true, and then we do this thing. Else we do something slightly different. So we'll do, if we take this and then dot build back not allowed. Otherwise we'll do and then dot build back allowed. All right. Okay, so then for node nn nodes, if nn dot taken, then this out plus so this will be nn dot adjacency dot size plus a space. Otherwise, this out, it's not taken, 1 plus a space. I think we're fine then. How do we do this? Okay. I think that's true, right? Okay. Okay, so this we're just getting wrong. That's fine. Dang it. Is the right answer 6 or 7? The answer is 6. They have the last case. Ah, come on. Very useful tool for those of you who aren't aware. CS Academy Graph Editor for when you don't want to draw out these graphs. Just do it for you. Okay. sometimes requires a little bit of untangling. So 1, 2, 3, 4, 5, and then we need this 8 here. Yeah, it's got to be. There's no other way of doing it, right? 1, 2, yeah. Oh, we never build back. That's why. Yeah, okay. All right, so then what do we say here? We say if n equals 2 and dot max nodes equals 2. I think that should just be fine. Yeah. And then cool, system dot out with out, replace all, and then let that close. I think we should be good. All right, we'll move on to E then. Power board. You have a rectangular board of size n by m. The n rows are numbered 1 to n from top to bottom. The m columns are numbered 1 to m from left to right. The cell at intersection of row I, column j, pretest passed, contains the number I to the power of j. Oh, okay. Find the number of distinct integers written on the board. What? 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 So mathy, I don't want to do it. Come on. Why is Codeforces down? Okay, so wait, am I doing really well or something? Wow. 33rd place, not bad actually. Okay. Why? Why do we have to do this? I don't want to do this. Dude, I don't want to do this. Guess we're doing it anyway. Okay, so most of these things are going to be duplicates. Probably. Maybe not. All right, so we've got like 1, 1, 1, 1, 1. Now we have powers of 2, so 2. Oh, I guess we should probably, this is easiest. Two to the 1, so 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 3 to the 1, 3 to the 2, 3 to the 3, 3 to 4, 3 to the 5. Okay, so this is interesting. So now we have 4 to the 1, 4 to the 2, 4 to the 3, 4 to the 4, 4 to the 5. So we only start at here. So these are all unique. So these are all unique. Okay, those are all unique. These are all unique. These are all unique. The 5s are all unique. 5 will get everything. What about 6? So 1, 6 to the 1, 6 to the 2, 6 to the 3, 6 to the 4, 6 to the 5. Well, it's not gonna, the 4s won't matter because 4s don't have any powers of 3 in them. If it's gonna have an even number of 2s and 3s, yeah, so the number has to be a factor of 6. So 4 builds off 2. 6 can build off 2 or 3, but we, oh wait, no, it can't. So it's gotta be a, like a square root. Like you take the, oh wait, what is it? So it's like x to the 1/2, x to the 1/3. Could be x to the 2/3. Yeah, so I guess you like take the GCD of exponents and then divide that out. Yeah, okay. So we can figure out where this maps to. So we'll get this problem for sure. We can figure out where it maps to. So now we know where it maps to. This is an easy contest. Okay. But now we have to figure out the ratio between these two things. So, oh, I guess this isn't where it maps to. This is like, this tells us like what, this tells us what row we care about. Yeah, let's think about this in a slightly different way. So what if we have like 2 to the, say like 2 to the 3 times 3 squared. That's a bad example. Maybe just like 2 times 3. Okay, so, this gets annoying, doesn't it? So what if we have 2 squared times 3 squared? No, 2 to the 3, 3 to the 3. How big is this number? Let's just do 2 to the 3 and 2 to the 4. Oh, do we care about all all other things. Man, this is gross. So we have 2 to the 4. I guess all that matters is this. So this is 4, 8, 12, 16, 20. Let's say 24. Okay, then we had 3, 6, 9, 12. 3, 6, 9, 12, 15. 15 plus 3 is 18. So this doesn't actually hit all of them. This hits 12 from this. Okay, but we also have 2. So we have 2, 4, 6, 8, 10, 12. We could imagine removing this line. Let's do that. So if we do this, then we hit the 4 and the 8, but not the 12. Or maybe the 12. I don't know. Let's say not the 12. Is it ever possible there are gaps that aren't hit? Ugh. Ugh. It is a disgusting problem. Oh my god, in 6 minutes. How speedy. Yeah, so how many rows might we care about? Surely like at most log n, right? No, because wait. Yeah, we only care about log n rows. Not only do we only care about log n rows, but there are like only 100 rows that aren't, or that are squares. Yeah, because there are only 1,000 things you can square that stay small enough. No, JK, 1,000. There are 1,000 rows that are not like original. Okay, hang on. Oh, is it that easy? Come on, please be that easy. How cool would that be? So if not square, cube, etc. Height, then it's just like m. Then just add m. Okay, otherwise, 1,000 times 10 to the 6 is 10 to the 9. Doesn't quite work, but we're almost there. What if we do cubes? There are only 100 cubes, so 100 times 10 to the 6. Yeah, we can probably get away with that. Bit messy, but okay. So if square, then start at m plus 1 to the end. Otherwise, we have a cube. So if cube, or if greater than or equal to cube, what do we do for greater than or equal to cube? If we are greater than or equal to a cube, then we have to do some stuff. We have to say what if we're greater than or equal to a cube? Oh, then we just iterate through everything. Yeah, so then just iterate through everything. Through all multiples. And check if it is in any of the other ones. Yeah, like check if it is. Okay. I think I understand how we're going to do this. So we're going to have something like, it's a single test case, right? Int height equals this, width equals this. All right, so y ants equals 1. For int y, oh, so then we need Boolean array hit equals new Boolean array. Height plus 1. So then we'll need static int house low, int base, int exponent. If base times ants is greater than max, then max, say. Okay, so yeah, so hit 1 equals true. So int y equals 2, y is less than or equal to height, y plus plus. So if hit at y, then continue. Otherwise, we know this y isn't hit. So yeah, so then I guess int max pow equals 1, while pow slow of y to the max pow plus 1, the max of height plus 1, is less than or equal to height, then max pow plus. All right, if max pow equals 1, then we can handle this pretty easily. Oh, so we need to mark all these as hit now. Yes. So we'll say hit at y is true. We'll handle this one. What is this doing? This is the next power of 2. So hit at pow slow of y to the max pow height plus 1 equals true as well. Okay. All right, so we handle everything getting hit now. So then at the end, 6 out ants, then we're good. Okay, so if this is the case, then we'll say ants plus equals width, because they're all unique. Otherwise, if max pow equals 2, then ants plus equals width, and then something else, and then continue. What is this other thing? So we need to handle, so we get 1, 2, 3, 4, 5, all the way up to n. What is n? N is, we'll say n is 5. Well, 6, 7, okay. And then this hits 2, 4, 6, 8, 10, 12, 14. Okay, so then ants plus equals width. So we get all of these minus, what's the overcount? Width over 2. Width is 5, we double count 2, yeah. Okay, all right, good. So otherwise, we have, this only happens about 100 times. Okay. Yeah. So, what should we do? Int array? Hash set. Oh, I guess, okay, so we'll assume we've added, oh, maybe we just don't even need to. Yeah, okay, so for int exponent equals, we'll do these things first. For exponent equals 3, exponent's less than or equal to max pow, exponent plus plus. And then we also have y is the base, okay. For int exponent multiplier equals 1, exponent multiplier is less than or equal to width plus, okay. So long to evaluate will be this will be exponent times exponent multiplier. Well, exponent is always, this only goes up to at most like 20 or so. So this can be an int, because this is at most 10 to the 6th. Yeah, so this is fine. Okay, so this is the number we're evaluating. Need to see if we've seen this before. Oh, we could probably do this with bit sets. Yeah, we could do this with bit sets. Okay, anyway, so if to eval is less than or equal to width, then continue. If 2 eval mod 2 equals 0, and 2 eval over 2 is less than or equal to width, and continue. Otherwise, we do some stuff, and then ands plus plus. Okay, so what is this other stuff? So for int I equals 3, I is less than the exponent, I plus plus. So this is order 20, so we're fine in runtime. So then we say if 2 eval mod I equals 0, and 2 eval over I is less than or equal to width, and we continue, well, or continue space, I guess, space. Yeah, so it should be good. I think that's it. Seven. Dang it. No, 5. Oh, cool. Because I'm like, debugging this is going to be a pain. Let's just cross our fingers and toes that we don't have to debug this. Because that would be... Oh, can you imagine? Don't want to have to debug this problem. Please don't have to debug this problem. Oh, it might be a long overflow if we get it wrong. Oh, you're kidding me. We should be fine though, right? Well, I guess it's super easy to test. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's fine! You're kidding me. You're kidding me. Long time equals system dot current time millis. This was so fast. Sys out system dot current minus time. Oh, you are kidding me. This is BS. Is it this POW slow? No. Why would it be the POW slow? This is so easy. Okay, how many times does this happen? This is the only slow part. This is literally the only slow part. It's got to be this. Totally passes in C++. 150. Okay, I predict 100. Why is it 150? It happens a couple times for the same things. Okay, can we break? We can break some of the time. No, we can't break. You're kidding me. This works in C++, dude. What if we make this and 1? Okay, we probably don't need to start at 1. we can start at the very least with plus 1 over exponent. Then we don't need this. Are you for real? Is that the same? Ends in 182. Oh wait, hang on. Oh my goodness. So that's this. What was it before? This is with plus 1 over exponent. Ah, dude. Okay, C++ it is. All right. Close all. File. This all is going to be in main. I don't even remember which problem this is. Okay. Should be pretty easy to convert to. Okay, so type def long or pound. I think it's type def long ll in height width cn height width. Is it height width? Yeah. Okay. We'll just do this later. LL this equals 1. Bool hit. To the 6, okay. That's fine. Oh, these should be. I think that's how you do it, if I remember correctly. Okay, so pow slow. Okay. So then we need int pow, or I guess, yeah, ll pow slow. I don't know. You put, or I guess. so slow? How do you time? Oh, I didn't rebuild it. Really? Okay. 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 So looks like we got to handle max pow equals 3 as well. This is annoying. Okay. So we get these two anyway. So now exponent equals 4. So now ants plus equals width. Okay. Ants minus equals width over 3. Ants minus equals... How many numbers are multiples? Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Then we have 3, 6, 9, 12, 15, 18, 21, 24, 27. Okay, so the first n over 3, we lose. Okay. Then, how many even things are there? N over 2. There are width over 2 of them. Yes. We lose all of the evens. Oh, but not quite, actually. We only lose a third of the evens. Yeah, so we lose 3, 1, 2. Yeah, so we lose. Okay, we lose 3, 6, 9. And then we also lose 6, 12, 18. Mobius inversion. And then we regain 6. So minus equals width over 3. And then ants plus equals width over 6. $182, and it's probably fast enough. It's got to be fast. Dude, this isn't fast enough. You're kidding me. It's got to be fast enough. Otherwise, we're doing 4. Okay. Alright, actually we should probably time it. Okay, so let's convert it to C++ since we've already done the work. Okay, and then this needs to be 4. Is that the difference? Why is it so slow? Why is it so slow? Shouldn't be this slow. We're doing speedy stuff. Okay, I guess we'll just try this Java. Then we might have to do it one more time. Submit E. It's like so close to the border here. No, we got test 1 right. Nope. We definitely get it right. Do we really not get it right? 0. Oh. Dang. Submit E. Go. Come on, you can do it. Come on. Okay, so we need 4 as well. Man, there cannot be that many things here. Okay, what about 4? So it's equal to 4. So we get this. This is 3. All right. So then we get with. We lose. Ants minus equals with. Over, is it really the slow POW? Is this it? It's gotta be this. Yeah, this is order 10 to the 6. Only happened 64 times. No, it's definitely this break. Okay. Okay, so this is 1, 2, 3. So width over 4, so we get every 4th. And then minus equals width over 4. Okay, and then ants plus equals width over 2. Because we, yeah, let's just do this on paper here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have 2, 4, 6, 8, 10, 12, 14, 16, 18. And then 3, 6, 3, 6, 9, 12, 15, 18, 21, 24, 27, and then we have 4, 8, 12, 16, 20, 24, 28, 32, 36. Okay, so we get, how many of these? So we get 4 and 8. So we get this, okay? And then we get every, so this is width over 2. We have 4, 8, 12, 4, 8, 12, oops, 16. Yeah, that's width over 2. We get every second. And then plus equals width over 2, or width over every 4. So these first ones over 4, yeah. Over 4, okay. So plus equals width over 4. So yeah, this is the second row, okay. And then we need the third row. So what is the third row? So third row is every fourth. 3, 6, 6. Will 6 be a multiple of 4? No. 4. So yeah, every fourth. So ants minus equals width over 4. But then some of these are double counted. It's going to be very messy. It's going to have like 4 parts of it. So ants plus equals width over 12. Yeah, this is every 12. Width over 12. Well, every 12 will always be a multiple of 2, right? Yes. If it's a multiple of 12, will definitely be a multiple of 2. So we don't actually care about the first row. Yeah. So this goes up to width times 2. Width over 6. I think this is going to be true. It's not saving any time. But it's getting so much more difficult. Why? Okay, we can probably get rid of this pow slow thing. Well, this is the worst case runtime. It's worth it. Let's try it. Let's try it. This problem is dumb. It passes! Okay, hang on. Let's just see. Where are we at? Oh, wait. Exponent at 4. This should be wrong. 2.3. Wait, why is this even right? It should be wrong. Yeah, okay. What is 3? Oh, okay. There we go. Fast enough. Fast enough. It's fast enough. Come on. What? It's so speedy, though. Okay, what does C++ do then? So we need this for case. And then we need to do this. Two, three, four. And then start at 5. .8 seconds for real? What if we're just not compiling optimally? Oh, Java. Okay. All right. Wait, what was the output though? Were we getting it right? 8.2, okay. Submit. E. Wrong answer? Oh, yeah. It's dumb. Time limit's way too tight. Okay, how are we doing? We're getting roasted by penalty points, aren't we? Yeah, 50th place. Rain boy, what are you doing? Rain boy, no, no, the legacy. Rain boy. Oh, maybe Rain boy's going for LGM. Rain boy. For those of you who don't know, Rain boy always will solve problems from hardest to easiest. I don't know. Wacky. Okay, playing around the table. There are n players numbered 1 to n sitting around a round table. The ith player sits to the... We definitely don't have time for this, but we'll give it a shot. The ith player sits to the right of the... Never mind. Okay. Players are... Yes, in a row. Okay. There are 2 to the n cards, each of which has an integer between 1 and n written on them. N squared cards. What? Yes. Okay, n squared cards with numbers 1 to the n. Yep, so like n suits, each up to n. Okay. Initially, these cards are distributed among all players, such that each one has exactly n. In one operation, each player chooses one of his cards and passes it to the player to his right. All actions are performed simultaneously. A player is called solid if all of his cards have have integer I written on them. Their objective is to reach a configuration in which everyone is solid. Find a way to do it using at most n squared minus n operations. You do not need, so chooses one card and passes it to the player to his right. You do not need to minimize the number of operations. What? Surely you can just... Can you not just pass? Oh, I see. Okay. So we're at the point where this problem still seems easy. So why is this difficult? So anytime you have one of your own cards, you keep it forever. Oh, problem. What if you have all of your cards? If you have all of your cards, you are a problem person. Yeah, because you still have to get rid of one. If you have your cards, you're in trouble because okay, so you have a bunch of players. Each player has n cards initially. And every turn you gotta have one card. Yeah. All right, thank you. Whoever wrote this, you did a great job. This is very well done. I appreciate it. So good job. Good job. Also, I think the person who wrote this was named Dark Cyan, which, yeah, look at this. Dark Cyan for coordination and problem reparation. What a name. What a name. That is a great handle. Dark Cyan. I love it. From ITMO. Very cool. I know it's the thing to do to hate on Russia at the moment, but ITMO's a cool school, you know. And Dark Cyan's a great name. So we're just gonna leave it at that. Okay. This would be a nice time to use like some sort of flow or something, because n is small finally, and it feels kind of like a flow sort of thing, right? You've got certain bottlenecks. You got to get everything to where it belongs. It's not obvious how you would do it. There are probably a lot of ways of getting wrong. Although, maybe flow isn't a good proof. Flow would kind of be cheese. So you have n people. You have a bunch of cards. What if you take n turns? Oh, what if we do n at a time? Good idea, good idea. Yes, that's a good idea. So can we swap these two? Swap, swap. And keep it. Swap, 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 swap. You can swap with two things that are adjacent. Anyway. Yeah, what if, okay, so what do you do if you have like, what do you do if you've got something like this? And then suppose you want to swap like this card here with this card here. How do you do that? So obviously you have to pass like, you gotta pass this one. Probably, you have to pass this one. So this thing will be passed n times. So this, like, this gets looped around, so we don't care. So you pass this one twice. But the problem is you've now passed this purple one twice. One, two. So purple's here. So you still have to get the purple over here, but what do you do here? Because this now has exactly what it needs. Man, that's annoying. I don't know. I don't even know how you would do it. Like even just with infinite turns. Because you're gonna mess something up. Like you can swap these two if you want. You can swap two things on the opposite sides of the circle. Can it be impossible? An answer always exists. So, okay, one observation is that there are n cards, and like not just one. Because if we have these just one, you wind up with kind of a problem. But yeah, because then you don't make any decisions, so it's just in a loop. Maybe we have to use like all n of them somehow. Oh, maybe we get one person with one of each card. So, yeah, what if we do that? Each person has one of each card. And then we go like to that state and then from that state. If each person has one of each card, then do all people have the same potential? Yes. Then all people are the same. Yeah. Oh, that's cool. Okay, so each person, you can't even read that. Each person to one of each card. And this is the middle state. So that's useful. Because if we can get to this from any state, then we can easily finish. Yeah, so how do you get to getting each person to have one of each? Well, this is easy enough, but the trick is like, how do you get there? People can have differing potentials, right? But you can swap. Oh, look at that. You can swap like 2 cards. So this purple can go to any person. So it's bipartite matching. Is it? Hang on. Okay, so we want all people to have the same potential, right? Because we want all people to have to give the same number of cards. Yeah, we want all people to have, well, what is a potential actually? Potential is, yeah, we want to wind up with like the parity being equal. Mod 6 for every card. That's the important part. Because if the parity is like too small, you have a problem. And if the parity is too big, you also have a problem. And the fact there are 6 cards makes it work mod 6. Okay, so I am convinced this problem is solvable if one was infinitely smart. Yeah, I don't have a solution yet. Cool problem though, cool problem. Very good set. Thumbs up, let's upvote it. What do you say? I thought it was a good contest. Well written, all around, very interesting problems. Well done, Dark Cyan, and Dark Cyan made it and prepped it. Okay, good job. Yeah, well done. Good set, good set. So, yeah, let's like more formalize what we actually need here. We want if you have like 6 turns. Oh wait, what if we change the colors? Whoa. What if we want everyone to have a 1, 2, 3, 4, 5, and 6 initially? Wait a minute. Does this work? We might wind up being just short. Okay, so, well, 0, 1, 2, 3, 4, 5. I think it winds up being like just perfect. We'll make like exactly this many, I think. Yeah, okay, so we need everyone to have, okay, we need each person to keep, yeah, so we need each person to keep 1 card. Okay, each person, second, each person gives 1 initial card to every person, to everyone, and then this happens a second time. But the second time we solve it. Okay. This is so cool. This is such a cool problem. I love it. Oh my goodness. This is an awesome problem. Okay, each person gives each initial card to everyone, and then it happens again. Okay, so how do we assign which card goes to which person? That's always possible, right? If you have 2 purple, yes. If 2 purple, they can go to 2 different people. So you have like, this is like person 1. This is probably going to be flow too. Person 1 will have a bunch of different colors. So you've got people. Each person will have one of each color. I guess, so these are like person comma color pairs, which match with each other. So you have person comma colors starting pairs and ending pairs. Is that right? Person comma color start and person comma color end. Yes. Okay, so you have like n. Let's say n is 4. So you have n here. So these things, one of them needs to go to person 1. One needs to go to person 2, one needs to go to person 3, one needs to go to person 4. So this is 1. So this is like fully connected. Okay, this is to person 1. This is to person 2. And so on. Then we have 3. And 4. We each have one of these, and these are the cards people end with. We have one of these. So you're going to give this card to one of the people. Each person gets one card. Okay, how do we know that the people end up with the right... Wait, we're not really using colors at all here. Oh, these are the person color pairs. Oh, so this... You can't distribute to all of these. This is not possible because this ruins the colors. Yeah, you can like start with a red and end up giving a blue. Because this is red, you could give a red to someone else. This is red. Yeah, you can... That doesn't make sense. Okay. So this is person color, and this is who we give it to. What do we need, like person give to pairs? And assign a color? Person, person, and assign a color. That's a good question. Person to person, and then assign a color. So what are the constraints here? We need to have, there are 4 colors, but we might want there to be more. Yeah, because each person is giving each other person one thing. One thing? One thing. Yeah, each person gives each other person one thing, and this happens twice. Second time is easy. The first time, each person gives each other person one thing. So yeah, how do we do that? So the question is, which color are you giving each person? A gives B. What does A give B? What does B give C? Etc. So you know what color each person has to end up with. Each person ends up with one of each color. There are other problems like this. This is a really good one to know. How to do this flow. Okay, I have to go to the bathroom. The joke I just made was funny, but if I repeat it, it won't be. So you'll just have to assume that I'm a very funny individual. Okay, so we can't, we know who can give who a color. Can you give two different people? Yeah, can Alice give two different people red? Maybe. Alice might be able to do that. But, okay, so we know how many colors each person has to give, how many colors each person has to take. This is 100% flow. Yeah, I don't know how to do it, but I definitely know it's flow. Okay, sure that on. Oh, don't you love my brother asked if I have oil to cook with. Yeah. Wait, what did I just leak here to the internet? Yeah, nothing important. Okay. In case you're wondering, I do have olive oil to cook with. Yeah, I don't know how to build a fully graph. Okay, no F for me. Brainboy got it? Ooh, in the nick of time too. Well done. That's a tricky problem. It's a very high quality set though, overall. Very, very nice, very nice. My congratulations to everybody who solved it and to the authors for coming up with such interesting problems. How about we talk about solutions, huh? Let's do it. Okay. Yes. Although I suspect, since this was so well prepared, there will almost certainly be an editorial out instantly, because if you put this much effort into your problems, you're definitely writing an editorial. But let's talk about it. So, problem A. In this problem, we have some integers, and we have to make an array where each of the elements are either 1 to n plus 1, or either 0 or less than n, or they're equal to n squared. And we have n plus 1 of them. So here's the observation. N minus 1 times n plus 1 is less than n squared, which means since the number of things is uniquely determinable, which they tell you right here, you have to print how many elements are equal to n squared. So since they tell you it's uniquely determinable, you just have to print anything that works, because that's the only one since they tell you, which is a nice hint. And what you could clearly do is make everything n minus 1, or n squared, and then use the rest to find the sum. So yeah, because like the sum of everything else can't equal 1n squared. So the number of n squareds you need is just like the floor of the division. Formally, it's just s divided by n squared, and that's the answer. Because like that number of n squareds is possible, and like clearly you can't use more than that, and if you use any less than that, it's not going to be possible to reach the sum. So that's the idea. What that looks like is these 3 lines of code right here. So very, very easy problem. Okay, that's problem A. Let's talk about problem B. Quality versus quantity. All right, so you need to pick some elements that are red and some elements that are blue, and you want the sum of the red elements to be more than the sum of the blue elements, but the number of red elements to be less than the number of blue elements. So in other words, you want the red elements to be like more densely packed in value. You want the red elements to have like a lot of value, the blue elements to have very little value. So I guess it should be somewhat obvious that you want the biggest elements to be red and the smallest elements to be blue. And then you want there to be more red than blue, which means, you want there to be fewer red than blue, which means you want to pick as many as possible, because if there are as many as possible and you have the valuable ones be red, then like this sum is going to be like the amount per element that the red ones have to be bigger than the blue ones will decrease if you have one more red, one more blue element. So initially, in order to satisfy this red-blue constraint, here, let's say we've got this. So let's say we have some array. We'll just make the number simple. So initially, to satisfy this constraint, let's say 3, 3. So these are the numbers. We'll pick the smallest blue element by itself. So for blue, we'll just have this 1. And then for red, we'll have nothing. Then we can add one more blue element and one more red element. So we have just the blue 1. Next, we'll add this blue 2, and then we'll add the red 3. And we keep doing this until either we run out of elements or the red elements are bigger. So now we have a 3 here and a 3 here. We add the 3, we add this 3. And still these sums are the same, so we have to keep going. We see this 3 here, so we add another 3, we add another 3. And now we've used these ones for the blue and these ones for the red. So what you can imagine doing is just cutting your array in half. And this is the best, like the most extreme the difference in sums could be, when you have all of the big ones here, all of the small ones here. It doesn't quite work if the number of elements is even though, so that case is a little bit different. Let's do an example for that. Here's an example. So you might think, oh, let's split it like this. We'll make these ones blue, these ones red. Problem is, then we have the same number of elements on each side, so we can't do that. So our split point would have to be here. However, you might think, oh, it doesn't work if you do this, because here this sum is 6, this sum is 4, so the blue sum is too big. But you can actually leave this one blank, and now you have a sum of 3 and a sum of 4. So this is an easy break case, which will help you get the problem correct. So yeah, if the number of elements is even, then we want the valuable red elements to be the suffix of the sorted array. We want the less valuable red elements, or less valuable blue, to be the prefix of the sorted array. And we want one more blue than red, and we want as many elements as possible. So all of those are greedy observations. So problem B, that looks like this. Read in n, read in the array. We sort the array, and then we add in all of these numbers. So if it's before this split point, we add it to S1. This n over 2 will be this split point here. So we add all of these things to S1 and this to S2. Because 4 over 2 is 2. So this is index 0, index 1, index 2. So all these get added to S1. This gets added to S2. However, we don't want this in S1 if it's even, because then we can have like 2 split points like this. And then we print yes or no. Okay, that's the solution to problem B. Very good. Moving on, problem C, factorials and powers of 2. Yeah, okay, so for this problem, you have some number, and you want to represent it as some factorials plus some powers of 2, and you want to do it in the fewest possible numbers of those powerful numbers. However, you can't use any factorial or power of 2 twice. Now, obviously, you would never use a power of 2 twice, because if you add a power of 2, if you use it 2 times, that's the same as using a different power of 2 one time, right? So if you use 4 twice, 4 plus 4, that's the same as just using 1/8. So you never do that. But that's not true for factorials. So 6 plus 6 is 12, but 12 by itself is not necessarily a factorial. In fact, it's not. So I don't think it's possible to do 12 into, we can check. Okay, it is possible to do 12. What about 48? Okay, well, it's hard to find a break case, but I can promise you they exist. Yeah, probably eventually if you keep, I don't know, maybe they exist, maybe they don't. But it's definitely easier to prove that my solution works if they exist. So here's the idea. If we have this constraint. So we can only use each factorial once. That's an important thing that we're going to abuse. And it turns out there aren't that many factorials. There are like 15 maybe. 15 factorial is 10 to the 12. Yeah, so there are 14. So the biggest factorial we would ever want is 14 factorial. So if we're interested in which possible factorials we could use, we know there are some factorials that we'll subtract and some that we won't. And the ones we subtract, we have 14 options. For each one, we can either subtract it or not subtract it. So that's 2 to the 14 possibilities of factorials we might want to subtract. 2 to the 14 is not actually that big. 2 to the 14. It's only 16,000. So, oh, sorry, I was covering this. My bad. We only have 16,000 possible combinations of factorials, of sets of factorials we might want to use. So 16,000 sets, and for each one, the powers of 2 that we'll use are very obvious, because to represent a number as a bunch of powers of 2, you just look at its representation in binary, because that's literally what it means. It's like, how do you represent this number as a series of powers of 2? So yeah, that is how you do it. You go through each one of these 16,000 possibilities, and then you say, if we subtract out all of these factorials, assuming the number we are left with is still positive, what powers of 2, what set of powers of 2 will add up to this? That's just the number of bits that are on in it, which is pop count in C++ or bit count in Java. Okay, yeah. Also, this probably doesn't matter. It almost certainly doesn't matter, but I start my factorials at 6 because 1 is a power of 2 and 2 is also a power of 2, so we can't use those twice. I don't think it matters though. Yeah, it doesn't matter, because you would never want to. I don't think. You would always just use 4 instead. But it's, I don't know, maybe it matters. So these factorials, this list of factorials is all the factorials from 6 to 14 factorial, worst case. So in fact, there aren't even 14 of them. There are like 12 of them. But yeah, that's the idea. So we'll look at these factorials here, and then we will say, we're gonna brute force which subset of those we use. And then we subtract them out, and then count the number of bits in this mask, which is the number of factorials we use, plus the number of bits in our sum, which is, after we've subtracted out these things from the factorial, we have some things left we have to make with powers of 2, and the number of bits in that number is the number of powers of 2 needed to make that thing. So that's how you do it. Yeah, so this bit mask is the number of factorials. This bit mask is the bit mask of which powers of 2 we pick. So yeah, very, very useful problem for bit operations. So I think it's very useful as a teaching tool in my bag of tricks for teaching people things now. Okay, weight the tree, problem D. We have a tree of n vertices numbered 1 to n. We know what a tree is. Okay, yeah. So for this problem, you've got a tree. You're going to assign weights to every node in the tree, and you want to maximize the number of nodes in the tree whose weight is equal to the sum of all of their adjacent elements' weight. So if my weight is 7 and my neighbors are 1, 2, and 4, then I'm like a good node. You want to maximize the number of good nodes. And if there are multiple ways of doing it, you want to minimize the sum of all of those weights And if there are multiple ways of doing that, you can do it in any way you want. And you also have to like figure out how to do it. So here's the observation. Since all of the weights are positive, okay, JK, we are doing this with paper. Slightly dirty paper, but that's all right. So since all of the weights are positive, let's look at some node that isn't a leaf node. Wait a minute, did I just get this problem wrong? No, I didn't. Yeah, I didn't get it wrong. Okay, so yeah, I'm right. Okay. If you aren't a leaf node, so let's look at this node here. That means you have at least 2 neighbors. Each neighbor has a value of at least 1 since the weights are positive. So this is like greater than or equal to 1, greater than 0 anyway. This is greater than 0. What that means is you can't have both one of your neighbors and yourself both be good nodes. Because if you're good, this means you're bigger than both of your neighbors, right? Because you're equal to their sum and both of them are positive. So if any internal node is good, that means all of that node's neighbors aren't, because all of that node's neighbors will be less than it. So what we have to do is like pick some nodes on a tree, and we can't pick any 2 nodes on a tree that are adjacent. Now, it's not just 2 coloring the tree. It's a common mistake people make. I have made it before, but I've since learned. Here is an example. This is like the T-bone example. It's kind of like a bone, I don't know. But this is a common graph. So if you 2 color the graph, you will pick these ones or these ones, but that doesn't work because you can pick this, 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 and this. So it doesn't work. There are a bunch of other cases. It gets way more complicated. You can't just special case this. But yeah, this is the idea. Sometimes you might have 2 adjacent nodes. You might not want to pick either of them because they have like very large prospects for not picking them. Yeah, in fact, it's possible you might have like a chain of 3 nodes where you don't want to pick any 3 of these, which might be a bit counterintuitive. But yeah, it's never true that you won't pick a node and all of its neighbors, but you might pick like some of them, right? So you might do this. But if you don't pick a node or any of its neighbors, you might as well just pick the node because it's free. That part doesn't matter. Okay, let's continue. So the important part here is we're going to do a DP. So the DP is like DP at some node, and also whether we can pick it, whether we're allowed to pick it. We can be allowed to pick some node and not necessarily pick it though. Because like for this A, we're allowed to pick it because we didn't pick its parent. Let's direct the nodes like this maybe. So this is the root. We chose to pick the root. We chose not to pick, or we weren't allowed to pick this because we chose one of its neighbors. So we're allowed to pick this one and this one. For this one, we do choose to pick it. For this one, we don't, even though we're allowed to, which means we're allowed to pick its children. For this one, we would choose to pick it if we play optimally. And the DP is quite simple. So if you aren't allowed to pick it, then you just don't count yourself. You give yourself a value of 1. And then for all of your neighbors, you give them a value, or you let them choose whether or not they want to be picked. And if you are allowed to pick yourself, you have 2 choices. So either you do pick yourself, and you get 1 point for yourself, but all of your neighbors are not allowed to pick themselves. Or you don't pick yourself, in which case you just call the other transition that you had earlier. And you do the same way as you did before. And you take whichever of those 2 answers gives you the better answer for this subtree. And that's the idea. So what does the code look like? It's pretty simple. Pretty simple. This is, which problem? This is problem D. Yeah. Oh, also I got it wrong. For the n equals 2 case, you have 2 nodes which are both leaves which can be equal. So yeah, you have to do that too. But that's it. Yeah, so you build the tree. The root is allowed to be picked if it wants. And there you go. And then I have this answer class to also minimize the cost. So yeah, This is like get the better of two answers. You can do this with a pair if you store the cost as negative, probably. And then this is just the max of two pairs, I think, in C++. That might not be totally correct, but you can fact check me on paper. Okay, so I have both a build back method and a DP method, but you might be able to do it in just one. It's possible that the, yeah, I might not actually need to call this DP method, but I do. Anyway, oh well. Yeah, so here are the two DPs. I kind of explained them earlier, so I won't go into them again, but that's the idea. So yeah, I guess I will explain them real quick. You can either take it, you count the node, or you can, and if you take it, then all of your kids are not allowed, and then you have to include your kids' answers in your subtree answer. Or you can not include this node, in which case all of your kids are allowed to be picked. Yep, and then you have to build back your answer, which is basically the same thing. So this is what happens if you're allowed to pick, and if you're not, then it's very simple. And that's the idea. Yeah, that's it. Okay, yep, cool. That's problem D. All right, problem E. This was a very annoying problem. It's possible you can do this with Mobius inversion. I thought the time limit was way too tight. Like I don't see why this couldn't have been like 2 seconds or something, but oh well. So the problem is you're given this board where this element here is 1 to the 1. This is 1 squared, 1 cubed, 1 to the 4th power, and so on. This element is 2 to the 1, 2 squared, 2 cubed, and so on. 3 to the 1, 3 squared, 3 cubed. You get the idea. Question is, in this grid, how many numbers are there? How many unique numbers are there? So in this case, you have 1, 2, 3, 4, 8, 9, 27. So you have 1, 2, 3, 4, 5, 6, 7 different numbers. But obviously, if you have a 4th row, it gets more interesting, right? Because this row starts with 4, and you already have a 4. So it's not just the ones that are duplicated. And the second number will be 16, which you don't have, but if you had one more column, you would have a 16. So yeah, we can make some observations here. Let me draw this out on in a comment. So here's what the board looks like. We've got some 1s, and then we have 2, 4, 8. Wait, what is this? This is powers of 2? Yeah. 16 and so on. So an easier way of thinking about this is we're just going to look at the exponents. Because we know like 2, so, okay. The only time things will conflict, the only time two numbers will be the same, is if they have like the same like base element. So if you have some number and you take like the GCD of all of its powers, you can like subtract it out from that number. In other words, we'll see like, yeah, like, how do I explain this? For some, oh, am I gonna fail samples for this? No, I won't. Yeah, I won't, okay. For some base element, like 2 will, if you imagine this were infinitely long, 2 would hit 2, it hits 2 squared, so it hits 4, hits 8, and so on. And like all of these elements, like their base element is 2. 2 is like the first one that hits them. And then you also have like like 6. So 6 is like 2 times 3. But this element will, or this will hit anything where the exponent on 2 and the exponent on 3 are the same. So for all of those things, if you take the GCD of all of their exponents, you can map that down to 1, 2, and 1, 3, because those two powers will be the same. So that's like every number has like a unique like base element, which our solution doesn't actually calculate, but you can imagine that it could, right? We could calculate that if we needed to, and it wouldn't be that hard. So that's like the idea there. Now, once we have that, we know that like all that matters is the power of the base element. So that simplifies everything by making all of the numbers much smaller, because now we're dealing with powers and things increase linearly rather than increasing exponentially. And if things are increasing exponentially, things get like way too big for us to actually store. So yeah, that cleans stuff up massively. So here, what we're interested in here is like this 2 row is really like 2 to the 1, 2 to the 2, 2 to the 3, 4, 5, 6, 7, and then 2 to the 8, right? So that's, I guess we'll go 2 to the 8, 2 to the 9. So this is like what the row, these are the exponents that we're interested in. And then if we have a 4 row, we'll have, the exponents will be 2 squared, which is 4, 2 to the 4, 6, 8, 10, 12, 14, 16, 18, and 20. No, just 18. So what you'll notice here is that all of these elements are duplicated. Yeah, so these ones we would ignore, or we would have to subtract out, but these ones we would count. How many of these get duplicated? Well, it turns out each of these elements will duplicate every other one of these elements, right? So the 2, the 4, the 6, and the 8, these all get counted twice. So what this means is if both like x and x squared are in the height, then we can count both of them in constant time. If just x is in the height range, if just x is between 1 and h, but x squared isn't, we can also count it in constant time. So we can handle a bunch of cases. So anytime x is x-like but not x squared, then we can handle it in constant time. This is order 1. If we have x and we have, this isn't x times 2, this is x squared, x to the power of 2. Where is that key on my keyboard? X to the power of 2. If we have x squared but not x cubed, we can also handle this in order 1. This is a bit more tricky, but it's not too bad. So we get all of the, yeah, so I guess this is just width, plus width. What is this? So this is plus width. We get the width, and also we get width, but we have to subtract out width over 2. So the first all of these things, like we'll get the powers of 1 to 9 here, and then we'll get 2 to 18, but we just double counted all of these ones. So we double counted 2, 4, 6, and 8. So this is width over 2. Okay. This should be good enough. I don't see any reason why this isn't a legit solution. For whatever reason, I guess apparently it's not. So you got to keep going. So we'll do x squared, or it goes up to x cubed. X cubed works, but x to the 4th does not. All right, so how does this work? So now we have the 3's. So we've got 3, 6, 9, 12, 15, 18, 21, 24, and 27. Yeah. Okay, so we still, for these ones, we get these. For these ones, we get these like we talked about. What about these? Okay, so we get their double, we get all W of them. So we get everything here, but there are some things we don't get. So every third one of these right here, we don't get. So we don't get 3, 6, or 9. So that's width over 3, so minus width over 3. Okay, also there are some of these that we don't get. So every 3 of these we don't get as well. So we don't get the 6, we don't get the 12, we don't get the 16. Or we don't get the 18. So that's every 3. So that's minus width over 3 again. However, we just double counted some things. So this 6 we subtracted out twice. So of the ones in this first row, every multiple of 6 we just double subtracted. So we have to add back in W over 6. Okay, this would be a great solution. Should totally pass. TLEs. So we do even more math on paper. So x to the 4th passes, but x to the 5th does not. How do we do this? So we've handled all of these. Okay, so we've handled the first 3 rows. Let's get the 4th row. So this is going to be, the exponents here will be 4, 8, 12, 16, 20, 24, 26, 26, 30. When do I stop? 4 times 9 is 36. What? Uh-oh, have I messed up? 24, 26, no, it's 28, 32, 36. Okay. All right, so what do we get for this? So we get the whole row. So this is plus W. We get this whole row here, but not really, because we don't get any of these things. So this is minus W. But it turns out we don't really need to subtract this first row, because all of these things are even. So it's really just the same as this. So we're going to ignore this first row, and we minus W for minus the second row here, because all of these are hit. So each of these ones are hit, but only the evens in this range are hit. So this is minus W over 2. Those are the elements here that get hit. All right, it's also possible some of these things will get hit. So which ones get hit here? Every multiple of 4, so every 4th one here. So this one, because it's 12, and 1, 2, 3, 4, this 24 are both also multiples of 4. So this is minus W over 4, because it's every 4th one in this is double counted. But now we've double subtracted some things. So this 12 here got double subtracted because it's here. And that's it, because the 24 wasn't part of this list. So the question is, in like what elements were part of both this group and every 4th element in this? And we're counting multiples of 12, right? Because it's 3 times 4. So all the multiples of 12 in this group, we need to double like unsubtract. So this is, we need to add back in the multiples of 12 in this group. And since this is every 2, this is multiples of 6. This is plus W over 6. Did I get that right? No. Oh yeah, I did. This term doesn't exist. Why not? Oh, because it is... Yeah, why does this term not exist? I think this term should exist. All right, bear with me, folks. So for this 4, we get all of them. And then we don't get W over 2 of them. So you don't get half of these. Yeah. Okay. And then we also don't get every 4th one of these. But we do. Yes, this is wrong. Oh, is this included here? Yeah, okay. Here we go. So width over 2 minus width over 4. Yeah, okay. I didn't explain it right. I just was looking at it wrong. Yeah, okay. So that works. So cool. So we have done all sorts of math, and then we submit this in Java and TLEs. So we convert to C++, get AC. The life of a Java programmer, am I right? Yeah, so that is one way of getting the problem right. Kind of lame though. Okay, so let's talk about my idea. Still in Q, okay. Let's talk about my idea for F. So, okay, greedy. I thought it would be flow, but I guess not. So one thing you can do here is, what's the problem, first of all? You have a bunch of players, and you have n players, in fact, and they're in a circle, and you have n squared cards. You have n cards. Each card is one of n colors, and you have n copies of each color. And these are, at first, like, randomly distributed among the players. Or not necessarily randomly, but, like, arbitrarily. They can determine who starts with which cards. Now, what you have to do is do some number of moves so that afterwards, each player has all of the cards of their color. And each turn, what happens is every player will pick one of their n cards and give it to the player to their right. So everyone rotates circularly by one card. But they can choose which card they give. They also have to give a card. They can't choose not to. So first of all, this is like a bit more difficult than you might anticipate. And like the reason for this is that if you have a solved set, then like sure, you're done. Because like if you have a solved set, like you want to be done. You want to just stop playing. But if someone else doesn't, you still have to pass one of your cards to someone, just like to somebody. And if you're passing one of your cards to somebody, then this card all of a sudden has to get back to you. So now you have to do n-1 more moves. But whoever doesn't have that solved set, like they didn't have a fully like working set. So it's not going to work for them. Like you can't just get this one card back to them and like fix yourself. Like it's just not going to happen. So you have to be careful. Like it's more difficult than you might think initially. So like how do we go about doing this? One strategy which is useful is we're going to have this intermediate state. So instead of trying to give everyone all of the cards they want, we're going to focus on giving everyone one copy of each card. Doing that is tricky, but once we do that, it's very convenient because from each person's perspective, everything looks the same. Like if you're colorblind, I guess, if you're colorblind, you solved it. You have all the same color. They're all gray. No, I'm kidding. But like if you're colorblind, or like if on each, like, hey, let's say on each card you write which person, like how many moves are left on this card, and then you sort those, everyone will have the same thing in front of them, right? Everyone has one card that they should keep and one card that everyone else should get. So that's the idea. You just have to do that initially. So then, yeah, because like what will happen is everyone will give the card that needs to be passed once. That'll happen once, and then everyone looks at the card that needs to be passed twice. They'll pass that card 2 times, and the one that needs to be passed 3 times, pass that one 3 times, etc. So everyone is like symmetric, and that would be a state which we can finish from. Okay, so how do we get there? Well, the nice part about this now is that now we have like incurred a bunch of freedom for ourselves. So we can like, if we have a purple card, this can literally go to any person we need it to. We can give it to the first person, the second person, the third person, because all of them need to end up with this purple card. So that's like the benefit of having this intermediate state. So basically what you have to figure out how to do is give the starting cards, give one of each of these to every person. Right, so every person has to distribute their hand to everyone else. If you have 2 purple cards, these purple cards have to go to 2 different people, which perfectly makes sense because you need every person to have 1 purple card, and you need to give one of your cards to each person. So that's the challenge. How do you figure out how to give, like how to have each person give 1 card to each other person in such a way that afterwards nobody has 2 copies of any color. And that is a challenge left to the reader. I think you can use flow, I would imagine. But it's possible you don't even need to, given that flow is not one of the problem tags. Okay. That's the solution, or that's the idea. I'm not all the way there. Okay, that is all the problems in this Div 2. I thought it was a great Div 2. I would recommend upvoting it, but up to you. Your vote, your choice. Yeah, I liked it. I just problem E, way too tight on the time limit, way too unnecessarily tight. Like, no, unless there's just a better solution. But yeah, I don't see it. Thanks for the contest authors. Dark Cyan, I love your name. I love your contest, except for your time limit on E. But I like your writing style, and I like that you're not guaranteeing things. It's a very good sign of a problem author. Just like get some Java testers and double all their time limits. Like that's just do that, please. Okay. Anyway, yeah. Thank you for watching. Have a great day, and hope your rating went up. Goodbye.